So very soon we are going to start our next session where we will have two talks. We already have one offline speaker, Professor. Then second talk will be by Professor Nicholas Jessa. It will be online talk, and that will start at 5 o'clock. So it will be half an hour break. Some of you who wish to visit a lab can go between 4:30 and 4:00. Okay. And you will get high tea packet that you can bring to talk at 5 o'clock. Some of you who are very keen can also see our labs after 6. Some faculties have agreed to stay up to 7. Okay. So if you are very keen, possible after 6. Okay. So I think we are just waiting for our director to come here so that we will. So I think at least we have seen one of them. Right? Is there anyone who has not seen any light? Oh, that's good. So they have been to at least one. If you have any questions, you can also talk to the management. A lot of faculty members are also here. If you have any questions, then feel free to ask. Okay? Don't feel oh, this question may not make sense. Feel free to ask them. Okay, so I think we are going to start the session, and Professor, our secure director, Professor Bhanudas, he will introduce our first speaker, Professor Lee.
So thank you and welcome to this session. It's a pleasure to introduce Professor Bimalendu from the Indian Association for the Cultivation of Science. He's a senior professor there. Professor Babe did PhD in the same institute, Indian Association for the Cultivation of Science. And after that, he did his postdoctoral research in the Weizmann Institute in Israel and in the Georgia Institute of Technology. And then he joined Physical Research Lab in Ahmedabad as a faculty member. And now for many years, he's been at the Indian Association for the Cultivation of Science. And he's one of India's leading atomic molecular optical physicists, and has done outstanding work in many areas, including quantum optics, cold atoms, and most recently on quantum computing. And his talk today is on quantum computing using an ion atom hybrid platform. I should tell you that the current leading platforms for quantum computing are trapped ions and neutral atoms. And so we really look forward to Professor Babe's talk, where he's going to talk about a hybrid system, a hybrid computer involving both these platforms, trapped ions and neutral atoms. So,
thank you very much, Professor Singh, for your kind words and introduction. And I'm very thankful to Security for this opportunity. It's a great honor for me to speak on this special occasion, that is World Quantum Day, also on the occasion of the celebration of the International Year of Quantum Science and Technology here at TCG Crest. So as you can see that the title of my talk is Quantum Computing in an Ion-Atom Hybrid System. And I would mostly speak about the basics of computing in the beginning. Then I will move to the hybrid platform. So the purpose of this talk is to propose an ion-atom hybrid quantum computing model. I'm a theoretician, so I'll talk mostly about the model system. To demonstrate a universal 2-qubit quantum gate operation in the system. So I talk about what is 2-qubit quantum gate and what is universal gate. Okay. So the question naturally arises that why ion atom hybrid system, as Professor Singh told you that one of the leading platforms for quantum computing is ionic system and another is atomic system separately, and they are being pursued for several years. But among the various quantum systems for quantum computing, the ion trap neutral atoms in optical tweezers and superconducting circuit QED system, as you just visited the superconducting circuit QED lab in Professor uh, Upendev's lab. So these are the most promising systems, and but so both ion traps and Rydberg atoms. So I talk about what is Rydberg atom, offer a lot of advantages. However, they have a few drawbacks. So the question is it possible to build a hybrid ion atom system for quantum computing, combining both ion traps and Rydberg atoms? So here is the model, our model. We consider an ion B plus in the trap, in the ion trap. This is a Paul trap, linear Paul trap. You might have heard about the ion traps. And then the two atoms are side by side along the axis of the trap. We place in the optical tweezers. So this atom A1 and A2, they are trapped in the optical tweezers. So there is the optical technology developed over the last 20 years or so, which is called optical tweezer technology, by which you can hold the single atoms in the tweezer and you can place them as you like, and you can develop an array of optical tweezers in 1D, in 2-dimensional, even in 3 dimensions. So this is experimentally possible, that you can bring in atoms as you wish, and you can place them at a distance. And so the summary of the main results, we demonstrate a 2-qubit controlled phase gate operation with 97% fidelity between two neutral atom qubits. Here are the two neutral atomic qubits at large separation larger than 20 micron, by utilizing ion-mediated interaction between the qubits. The mediated interaction exceeds the direct interaction, leading to Rydberg blockade at large separation. So you have heard several terminologies. What is Rydberg blockade and what is fidelity? So I will explain. So here is the plan of my talks. First, I would talk about some basics about quantum computing. Then I will give an overview on ion trap and Rydberg atom quantum computing, our proposed model, as I just told you. So I discuss more about the model. Ion-mediated interaction is used for 2-qubit quantum gates. So this is our proposal. Then results and discussions and further studies. Okay. So some basics about quantum computing. As you know that classical computing works by utilizing bits and gates. Those are classical gates of electronic circuit. In quantum world, we use, instead of bits, we use what is called qubit. So you have heard about spin. Spin is a qubit. If you consider spin half, electron has spin half. So electron you can think of as a qubit also. If you utilize electrons spin, instead of spin, there can be pseudo spin. You can think of any two-level system, two-state system, two quantum state system can be used as a pseudo spin. And here I am considering a two-level atom. It could be a two-level molecule or two-level two-level superconducting circuit QED system. Any two-level system can be used as qubits. And you can describe its quantum dynamics in terms of Pauli spin operators. Okay. Spin, by the way, spin is a completely non-classical concept. Okay. You cannot have in the classical world spin. So when you have a two-level atom, so this is a non-classical object. Okay. And you can think of this as zero state. And this is one state. As in classical computing, we use 0 and 1 bits. This can a two-state system, so you can represent it as a vector, 1 0 and 1. So when the system is in 0, it can be described by this quantity and that. And so any two-state system you can describe in terms of what is called Pauli spin algebra. So 1 and 2 qubit quantum gate operation is done by manipulating any arbitrary superposition of 1 and 2. So this is the difference between the classical world and the quantum world, that you can have any superposition of the state, which is not possible in the electronic computer, classical computer. And you can manipulate those superposition states, and then you can encode information in the superposition state. And this makes all the difference. But by the way, not only in single qubit, you can have multiple qubits spatially separated, and you can make superposition. That is called entanglement. Okay. If two qubits are separated, here is one qubit here and there, and by somehow you can make a correlation between them. Even if they don't interact, they can be coupled through quantum channel. Okay, and that is called entanglement. And by quantum gate operations, you can manipulate entangled states. Single qubit, there is no entanglement, there is only superposition. And you can utilize that as a resource for your quantum computation. So good qubits, what are the good qubits? So in order to, so this superposition state, by and large, is not naturally available to us. In atomic systems or in subatomic systems, you have that, but you cannot utilize all the time for the quantum information processing. So you have to prepare a superposition state. That takes some time. So there is a time of preparation. So a good qubit is that qubit for which it's superposed, the lifetime of the superposition. If you prepare a superposed state, it will stay some time. And that time is typically of the order of microsecond or nanosecond, depending on what kind of qubits you use. But when you prepare this state, you will use some pulses, some electronics, and that will take some time. So a good qubit is that qubit for which the lifetime of the superposition is much larger than your preparation time. Otherwise, you cannot do any computation. Okay, so that is called a good qubit. And for atomic and ionic qubits, gate operation is performed by applying laser pulses on the system. Even in superconducting circuit qubits, as you have just seen in the lab, there also they use pulses, but those are in the microwave pulses. In case of atomic and ionic qubits, you have to use optical pulses in most cases, or microwave pulses in some cases. So this, if you consider an atomic qubit or ionic qubit, then we can use lasers to create superposition between the two states. And that interaction is governed by this Hamiltonian. You must have known about the Hamiltonian dynamics. In classical mechanics also, we have Hamiltonian dynamics. In quantum mechanics, we have Hamiltonian dynamics. But there is a difference. There is a H cross everywhere. So I have not put H cross, but this should be a H cross here. H is the Planck's constant. So this Hamiltonian is written under rotating wave and dipole approximation. These are some terminologies. So that is, so this delta stands for the ledger, the tuning of the ledger from the qubit transition frequency. So there is a transition frequency 0 to 1, and this is qubit frequency, and this is ledger frequency, so this is the delta. And this sigma z is the Pauli Z operator, which is actually the outer product of this 0, 0 state, which is actually population in the 0 state and minus the population in the 1 state. And that Pauli spin operator you can describe by this 2 by 2 matrix, because these are the outer product of these states, bracket notations. So you get this 2 by 2 matrix. Out of this 2 by 2 column vectors, you can form 2 by 2 matrices. And this is identity operator. And then this sigma plus is this operator. This what sigma plus does, you can see that this from this outer product. If you operate on 0, it will give you 1 state. If you operate it on 1, it will give you 0 state. And this is the form of the 2 by 2 matrix. And this is the coupling constant between the ledger and the qubit. It is called the Rabi frequency. And this phi is a ledger, because ledger, this is the interaction between the ledger and the qubit. So ledger amplitude can be a complex variable, complex quantity. So ledger can have a phase. So this is a phase. Ledger intensity, when you make intensity, then you have mod square of the electric amplitude, then you have a real number. So this is the Hamiltonian which will govern this gate operation. Okay. And in order to, okay, let us move on. So now I describe what is called single qubit gate. Single qubit, you have a qubit, and what you want to do by gate operation, you want to make any superposition state as you like. Okay. So it is possible by applying ledger pulses of certain duration. So typical ledger pulses is square pulses or any kind of pulses, but you have to control its time of interaction. Why? Now you can see. So this gate is described by this unitary operator. In case of single qubit, these are 2 by 2 matrices. And suppose you have initially prepared the state in state I, and if you operate it for a particular time duration capital T, then it will give you another state F. And so this ut is given by this Hamiltonian dynamics. Okay, so you integrate over this h of t, what I have just said. So then if you operate on that, so by the way, this spin algebra for qubit 2 by 2 matrices, you have exact analytical expressions for the evolution. So this is a good thing about the qubit, about the spin operators. So you can express this final state in an analytical form this way, and this theta, this can be controlled by this pulse duration and other parameters in the system. What are the parameters? We have this detuning parameter, ledger frequency detuning. You have this coupling constant, Rabi frequency, and you have this theta is the phase, which is actually half of this beta t, where beta is given by this quantity, square root of. So this is frequency unit. Frequency into time is a dimensionless quantity. So this is a theta. So you have to note this half factor. And if this beta t, if it is some pi into some number, new number, then we call it a new pi pulse. Okay. And new can be an integer or a fraction. And this theta is half of that new pi pulse. Okay. So then what you can see that if you have prepared a pulse in such a way that this theta is just pi or pi by 2 and delta equal to 0, then you can prepare any state. You can just by tuning those parameters. So experimentally it is possible. And if you do several of this kind of operations, you can do computing, because if you have encoded information in the states, in the superposition state or different states. So one of the important single qubit gates is what is called Hadamard gate. So it is given by this operator H. H is not here Hamiltonian, but this unitary operator for gate, single qubit gate. If it operates on this 0 state, lower state, it will give you a superposition state between 0 and 1. If it operates on 1, then it will give you the antisymmetric combination of 0 and 1. And this Hadamard gate you can express as a 2 by 2 matrix. Just single qubit gate operations are not enough to do actually real life computation. You need to have multi-qubit gates operation. Okay, you have to address several gates, several qubits at the same time, and those qubits can be in a superposition. So if 2 qubits are in superpositions, and that 2 qubits can be specially separated, that is entanglement. Okay, so you have to manipulate entanglement between the 2 qubits, and that is done by what is called 2 qubit gate. And you can have 3 qubit gates also, similarly multi qubit gates, but most important are the single qubit and 2 qubit. So if you have single qubit gates and 2 qubit gates at your disposal, then you can build a quantum computer, a prototype quantum computer. That's how people have done. And so this, so earlier in the case of single qubit gate, you had only 2 by 2 states, this 2 by 2 column vector. Okay, and now if you combine 2 qubits, then you will get outer product of this state 0 and 0, and this will give you by tensorial operation. So you have this 4 by 4 component vector. Okay, so you have this kind of so you have then 4 bases in case of 2 qubit. In case of 3 qubit, how many bases you will have? 2 to the power 3. So if you have n qubit, if you have to deal with 2 to the power n states. Okay, so these are the basis states, primary states, and then you have superposition of these states, and you have to manipulate those superposition as you like. Okay, arbitrary superposition. Okay. So in 2 qubit gate operation, the first qubit is called control, and the second one is called target. So depending on the control, first qubit. So here you have first qubit, and here you have second qubit. And if you use the first qubit as the control qubit, and it will control the target one. And then depending on the state of the control, you can change the state of the second qubit, that is target qubit, and that is called 2 qubit gate operation. Okay, and one such gate operation is called control jet gate, and another is the control NOT gate. Okay, and these control jet gate is that gate where if you have initially 0 0, it will remain 0 0. If you have 0 1, it will remain so. But when you have 1 1, then it will acquire a phase pi, which will give you -1 sign. Okay, so this is called control jet gate. Another gate is called control NOT gate, which is if the first qubit is 1, then second qubit will flip its state from 0 to 1. So, and 1 will go from 1 will become 0, and the first qubit state will remain the same. So this is called control NOT gate. These two gates are universal gates in the sense that if you prepare a gate, if you have this operation, you can prepare any superposition state of the 2 qubits utilizing this either. And these two CZ gate and C NOT gate, they are also related. Either of them can be used as universal gate. If you because by combining CZ and single qubit gate, you can make CNOT gate. By the way, what is 2-qubit gate? You cannot decompose the 2-qubit gate into the product of the single qubit gates. So 2-qubit gates are unique. They are not. They cannot be written as the product of the single qubit gates. So one CZ gate is this one. It will be 4x4 matrix, and it is the last. If you so this stands for 0 0 0 1 1 0 state and 1 1 state. And the CNOT gate, it will flip the state of the second qubit. So now I give you an overview of the ion and Rydberg atom quantum computing. So trapped ions serve as excellent qubits. So trapped for several hours. If you trap them in the ion trap, they will remain there for several hours to even days. Okay. And coherence time is, what is coherence time? That lifetime of the superposition state. Okay. That is typically millisecond to second, or it's enough, because in electronic processing, you can do fast processing of the order of microsecond order. So this is enough for doing thousands of operations in millisecond or second order. Individually addressable with laser. So because typically in ion trap, if you have an array of ions in the trap, in a linear Paul trap, and typical separation is 5 micron, and laser beam waste is typically of the order of few micron, or even less for good laser. So you can pinpoint your laser at a particular ion, and you can address them. Okay. And Coulomb interaction, so they are ions, so they interact strongly by Coulomb repulsion. And Coulomb interaction, along with harmonic motion of the ions, when ions are trapped, they are trapped in a harmonic potential, because this trapping system will generate a potential. It's like a bowl for keeping the ions in the bowl. So then this harmonic motion of the ions give rise to what is called phonon. You have heard, might have heard about phonon. Phonon are the vibrational modes when you have harmonic oscillations, and you quantize them, so they behave like some quasi particles, and these are called phonon. Okay. So these can be utilized for any 2-qubit gate operation, and people have demonstrated gate operation in ion trap quantum computing. Ion trap has all the good features as a reliable quantum architecture for quantum computing, except perhaps scaling. People are trying to scale up for many ions. And for quantum dynamic of trapped ions, so I would refer this. This is reviews of modern physics. So you can see that this is a good article. And for experimental issues in quantum computing with ions, you can look at this reference. This is called for Journal of Research of NIST. So. So next, another platform most useful is Rydberg atom platform. And this, over the last 2 decades, these Rydberg atoms in an array of optical tweezers have emerged as a viable quantum platform for exploring quantum computation and quantum simulations. Another purpose of making this kind of quantum architecture is to simulate any quantum simulate any many body system. So that is a separate topic. So not today's topic of today's discussion. So so scaling properties of the Rydberg atoms is very good, because unlike ions, because ions interact very strongly. If you bring in more and more ions, then there will be more and more phonon modes, and that complicate actually system. But for Rydberg atoms, that complication is not there. So one can easily scale up Rydberg system. So there are some properties, excellent properties of Rydberg atoms. So what is a Rydberg atom? Have you heard about it? So I hope that hydrogen, its atomic structure is like hydrogen-like structure, because there is a core in the atom, and there is an outer electron which is far away from the core, then it behaves almost like an hydrogen atom. So you can describe its energy eigenstates like hydrogenic energy eigenstates almost, and its energy eigenvalues. But so you know that the Rydberg formula, it goes as the binding energy of the electron, it goes as 1 by n to the power n square. So similarly, if you look at the properties of the hydrogen, so its orbit size goes as n to the power 2. So n is the principal quantum number. Okay? And the binding energy goes as n to the power minus 2 radiative lifetime. So this is important for doing quantum computing. Its lifetime becomes huge, very large, of the order of 100 microseconds. Okay, if you prepare a Rydberg atom in the principal quantum number of the order of 100, then its lifetime is of the order of 100 microseconds. And polarizability goes as n to the power 7. So this is also important for us. So you can look at some references here. So three most important quantum computing platforms are the following. One is superconducting circuit qubit and the ion trap Rydberg atom. So superconducting qubit, it uses actually anharmonic oscillator. So when you have anharmonic oscillators, unlike harmonic oscillators, the energy spacing between the different quantum states are different. So then you choose the lowest two anharmonic oscillator state as your qubit. That is what the superconducting circuit qubit. And so these are called actually artificial atom, and they are coupled to microwave photons for doing quantum gate operation. So in a sense, this is also a hybrid system, superconducting circuit QED, because you have artificial atom and you have microwave photons. So microwave photons you can also use for quantum computing. That's what this Amazon has done. Recently, Amazon announced a quantum processor using the state of the photons. That is called CAT states, some special states of the field. And so these different types of processors have been announced by IBM, Google, and Amazon using superconducting circuit QED system. And the prototype quantum computers based on this system, superconducting circuitry, are already in place. And for a review, I would refer this Nature Physics paper for you. And then second one is ion trap quantum computer. So early works performed by many stalwarts, Wineland, Sirac, Joller, Malmer, and many others. And quantum logic on an integrated ionic platform. For that, you can look at this reference. And Rydberg atoms, so these have emerged for the last 2 decades. This is a recent one. So ground state qubits you can trap in the optical tweezers, not in the Rydberg state, but you can couple ground state qubit to Rydberg state for doing quantum computation. So this is how the gate operations have been already demonstrated in Rydberg. So here is our proposed model. So I have already discussed this. So these are two dissimilar systems, highly, because one is ion trap, another is atom system. Their frequencies are different. So typically the ion trap, this oscillation frequency is of megahertz order, but in the optical tweezer, when you trap atoms, the typical oscillation frequency is 10 kilohertz order. Okay? And their trap sizes are different. So when I say trap size, it is actually basically the size of the ground state wave function. So how do you measure the size of a wave function? It is actually width of the, because you know that harmonic oscillator ground state is a Gaussian. Yeah. So you have Gaussian some width. So this is how the trap size, the effective trap size is defined. Okay. And I mean, for quantum computing, it physically it can be very large, but what is the size of that trapping size of that effective trapping size? Because these traps are harmonic traps. And you have then ion has different phonon modes, and atomic motion, they are different. So how to combine these two for developing a hybrid quantum system? So this is what we are asking ourselves this question, and we are looking at this. So we will use then two ground state hyperpine state. So by the way, what is hyperpine quantum number? You know the fine structure, you know. This is LS interaction between the orbital angular momentum and the spin angular momentum. When you include the nuclear spin, because nucleus has spin, and you include the electronic spin, that is electrons spin and orbital angular momentum and its spin, that forms what is called hyperpine quantum number. Okay? So this is typically this all the ions, this kind of single electron atoms or ions, they have hyperpine quantum numbers, hyperpine states, because nuclear spin is not isolated, or nuclear spin is coupled to the electronic spin. Okay, and then you have you can choose any two ground state hyperpine states as the qubit. Why ground state? Because ground state is a long-lived state. So these are very good qubit. Okay, because ground state, they can live for second, or unless there is collision or other thing, then you isolated the atoms. Okay, so you can prepare a good qubit out of atomic neutral atoms or ions. And but typically people don't use excited state. We use only hyperpine states of the atoms. And in our proposal, what we consider two hyperpine ground states of the atoms at the qubit, and we don't consider the internal state, what is in the electronic state, but electronic state is in state G. We don't consider this ion as a qubit as far as internal states are concerned for this proposal. And this is a Rydberg state with principal quantum number n equal to 100. So what we demonstrate here, we demonstrate two qubit gate operation. This is a little bit technical, so I would not go into detail, but I would try to convey you the essential message here. So as I said that to do quantum gate operation, you need laser pulses. So this is a typical laser pulse, this square wave pulses. So I have a control qubit here. So previously, so these two atoms, they are two qubits. In between there is an ion. I am using this ion to mediate interaction between the two atoms. So the purpose of placing this ion is to just to mediate an interaction, to enhance the interaction between the two atoms, so that at large separation they interact. So this is what, so this ion has some passive role here. So then this is the two hyperpine states of the atoms used as qubit, and there is Rydberg atoms. So when one atom is raised to Rydberg, very highly excited state, Rydberg state, another atom, they interact very strongly even at a separation of say micron order separation, 1 micron or several micron. So typically, if atoms are in the ground state, they interact at very short range, typically of the order of nanometer, not larger than nanometer. So if they interact very nanometer, it's not very useful because you cannot manipulate. So you need to have two qubits largely separated so that you can address individually by lasers. So this is what we are doing here. So what we do, we give a pulse on the first qubit, this first pulse. On the second qubit, we apply a 2 pi pulse. So earlier I said what is pi pulse, what is 2 pi pulse. And then finally we give another pulse here. And here we demonstrate how it works. So as I described in the Hamiltonian dynamics, so it will give you Hamiltonian dynamics. So when two qubits are in the Rydberg state, then there is a large shift of the Rydberg level because of the interaction, and that forbids actually to have two atoms simultaneously in the Rydberg state. This is called Rydberg blockade. If one atom is in the Rydberg state, and if you try to raise another atom to the Rydberg state, then either of the atoms will remain in the Rydberg, other state will not go to Rydberg state. So this is called Rydberg blockade, and that is, this mechanism is used here. But in our case, what we have shown that it is possible to have Rydberg strong interaction even at a separation of 20 micron. Typically, Rydberg blockade radius is of the order of 3 micron, 3 to 4 micron. Okay. So I skip this here. Here, what we are showing that after every pulse, what will be the state of the atom and two atoms in the 2 qubit states. And what is this Rydberg ion-Rydberg atom interaction? So this, if there is one ion is charged particle and interacting with a neutral atom. So this interaction goes as actually 1 by r to the power 4. So this you can easily understand, because there is an ion, it will generate an electric field. So this atom will see this electric field. So this electric field will polarize the atom. So then you have a induced dipole moment in the atom. So dipole moment, since it is induced dipole moment, it will be proportional to the electric field. Electric field goes as 1 by r square, and that dipole moment will interact with the atom at that point atomic. So dipole moment, this interaction is minus the dipole moment, dot product of the dipole moment and the electric field. So you have electric field is coming twice. So then you have electric field square, it will go. And it will be proportional to the polarizability. Earlier I said that the polarizability goes as n to the power 7. So if you raise an atom to a highly excited Rydberg state, say n equal to 100, then its polarizability will be increased by what factor? It will be increased by 100 to the power 7, which is 10 to the power 14 order. So it's a huge enhancement. And if you have huge enhancement in this interaction, even they are separated at a large distance, they will interact very strongly, and that will lead to what is called Rydberg blockade. Blockade means the interaction will be a shift. It will give a shift in the energy level. So this is some technical part that we expound this one. So we are considering a one-dimensional, so we are using this Z. So this is the atomic position jth atom, and this is the ionic position. So this is the distance between the atom and ion. It goes as 1 by r to the power 4. So they are at very large separation. So what we do expand this up to second order or first order or second order. So when we expand this, we get a small parameter. This is the atomic trapping size, which is actually the width of the ground state wave function. And this is the atomic position, which is a very large distance, atom ion distance. So this is a small parameter of the order of 10 to the power 1. So when you have a small parameter in your description of the dynamics, then you can use it as a perturbation. So we retain them up to first order. So ionic position, it is making quantum motion, harmonic motion. So then you can describe in terms of the creation of when you do field quantization, you get the description in terms of the operators which are called annihilation creation, phonon creation and annihilation operators. If you quantize the electromagnetic field, then you can get the description in terms of photons you have. So we describe this ionic motion position in terms of phonon or the. So then this is also some technical part. We do expansion, and so we do perturbative expansion, which is what is called Magnus expansion. If you have in the evolution operator two kinds of operators, and if you have time dependence, then two operators at different times, they actually don't commute, and that's you can expand. So we expand it up to second order, and then we get an effective Hamiltonian. And so this is published in last December. So here we are showing the evidences, that numerical evidence that actually this is possible, and to have 2-qubit quantum gate. So when you have the pulse one, first pulse, it will act on the first qubit. And if you have this is pi pulse, the pi pulse means it will take this atom to here. So this pulse is used only when the atom is in 1, not in 0. So when you have 0, 0, both, nothing will happen. So it is like a control Z gate or control NOT gate. So when it is in 1, then it will go to the after pi pulse on the first atom, it will go to the Rydberg state 1. Then you apply second pulse, twice pi pulse. So if it is in the 0, it will not be coupled to R. When it is 1, it will be coupled to R. But because of the Rydberg blockade, even if you switch on this laser 2 pi pulse, both atoms cannot be in the Rydberg atoms, either of them. Okay, so this is called Rydberg blockade. So this is how we are performing this gate operation. This is the atom 1. So Hamiltonian will change accordingly as you go on applying pulses. So you have different Hamiltonian, and both atoms are in 1, and you have both pulses are switched on. Then you have this Rydberg interaction, and you have Rydberg also mediated interaction. So here we are numerically, we have done numerical simulation. So this is to exact calculations, and we have shown that this ultimately you get a control Z gate, or what is control Z gate we have described, with fidelity 99 fidelity, like efficiency, how efficient it is, because actually this gate is a 4x4 matrix in case of. So this is mathematically exact gate, but experimentally you don't get that when you do calculation. There are some errors. So there are several sources of errors. One source is the spontaneous emission of the Rydberg atom, and we consider this spontaneous emission from the Rydberg atom. Then the exact gate fidelity will not be the 100%, not f goes 0 to 1. So it is 0.97, which is 97%. Okay. How much time I have? Okay, so I will wind up. Okay, so then what we have done further studies, we calculated also phonon distribution, because we have a 3-party entangled state, because you have 2 atoms and you have 1 ion. So ion is moving, harmonically moving. And when you have 1 atom excited to Rydberg state, then there is huge interaction between ion and atom because of the increase of the polarizability, and that gives a perturbation to the ionic motion. So then this phonon or oscillation changes. And when you have then another atom, so that is also excited to the Rydberg atom, then you have actually ion at that atomic state qubit and ionic phonon and another atom's qubit state. They are in a superposition state, all 3. So then we can do what is called projective measurement. We can measure the phonon distribution, how phonon distribution changes. So initially, if we consider phonon is prepared in the 0 state, that is the ground state in the harmonic oscillation of the phonon. So initially, and then after this first pi pulse, we have this kind of, and after second pi pulse, then the both this ion atom interactions will affect the phonon distribution. The phonon distribution changes, and after the last pi pulse, what the last pi pulse will do, this control atom will come back to the its initial state. So initial state goes to Rydberg state, the second atom will go to the Rydberg state, and finally this atom will, but the second atom will not go, actually it will not go. It will try to go, but it cannot because of the Rydberg blockade. Okay, so this kind of phonon distribution, so ultimately it will make a round trip, the ion, it will try to go to the same stage, but then you have a small difference in the, and similarly, if we prepare the ion in the one state, one phonon state, then after pi pulse you have this, and then it will, so this actually after this 2 pi pulse, what this 2 pi pulse will do, it will take the second atom to the Rydberg state, and it will again take it to its initial state. The pi will take 0 to 1. If you have 2 pi pulse, then it will take, but with a minus sign. This is what this non-classical spin dynamics gives you. Okay, this because two-state system is an object which is completely quantum mechanical. Okay, so this is what we get, and the people who contributed, my group members. So Shubhra, she is a third-year PhD student, and Shubhanko, he has already obtained a PhD in 2023 in working as research associate, and he is a second-year PhD student, and she obtained a PhD last December. She is also working as a research associate, and she did her PhD in quantum optics. So she has some expertise on quantum optics, and he has learned some about quantum computing, particularly quantum error correction, and he worked on fermionic atoms and many-body system, lattice models, and so this work is mainly her PhD work, part of her PhD work. So if I have some time, I can speak a little bit, 2-3 minutes. So now it is what we are trying next. What is our next step? Okay, and to scale up this system, so and to make it really a good hybrid system. So we are trying to make the quantum gate between atom and ion. And then you have atom-atom quantum gate, atom-ion quantum gate, and then 3-qubit quantum gate. For this, we are considering this rubidium atom and beryllium ion. In the earlier work, we considered rubidium atom and calcium ion. And so this, we are considering this n equal to 120, the principal quantum number. And this separation is along the x-axis. It's about few micron, 3 or 4 micron. Then we have found that because of this strong interaction between the atom and ion, not only its equilibrium position will be shifted, but the harmonic trapping frequency will change. And here it is the frequency shift. So you see that initially it was 11.2 megahertz. Then at 4 micron, it is about 10. So it is about 2 megahertz or 1.5 megahertz shift. It's a huge shift. So using this shift, we want to make quantum gate like 2 qubit. So this is possible because if you have this 0 state, then because of the large interaction, there will be no change in the qubit. And If you have one state, then there is no interaction practically, then it will make change. Okay, so this is like control NOT gate. Okay, if I have one depending on one state, the qubit state will change the atomic. So that's also, this is the first time I'm presenting this as an idea, and we are working on it. That and then next step is to bring in more atoms, because in a two-dimensional plane, so we have now two atoms, one ion in linear chains, and we can bring in two atoms. So we can scale up it easily, and that's how our plan is to work on that. So this is what I wanted to tell you. Thank you very much for your attention.
Thank you very much. Questions? Yes. Yes.
Your very initial slides, you mentioned good qubits, right? Whenever we are preparing the superpositions, so for getting a good qubits, like you said that we need to know the lifetime of superposition. So sir, how could we measure the lifetime of superposition?
Experimentally, how we could measure by, so maybe Bhupenda will tell more about his experimental methodology. So
You know, the two states, and you can apply a delay pulse to see how the population of this excited state changes. Initially, you kick it up there from 0 to 1. So you measure the population, you get 100% there. If you delay from that for the measurement, you kick it up, but you delay for the measurement, you see that the population gradually comes down. You can split it to the exponential, then you can get the data. That's the typical time it stays in the system.
Sir, can you go back to your second slide? I mean, where you showed the Hamiltonian?
yeah,
This one. In the Hamiltonian that you have chosen, it's for your research work. Here you have used the Pauli Z operator and sigma plus. So can this research work can also be done by using other Pauli operators like I sigma y or sigma x, or is it defined for this particularly defined for this research work? Or can we use other two Pauli operators also, define in Hamiltonian accordingly?
so in semi-classical theory, then if y equal to 0, then you have sigma plus sigma minus, just then it is sigma x.
Okay. Okay.
Okay.
Yes.
And if you have different phase, if you can make it sigma plus minus sigma minus, then you have sigma y. So, but just playing on the phase, okay, it's possible.
Any further questions? So if not, I mean, let's thank Professor Bimalendu.
Some of you who have not gone to quantum sensing lab can go there. And I Tanmay is here. Yeah. So he will show to some of you his lab. And I think other rest of you can go and have your snacks. And we'll gather here again at 5 o'clock for the next.